Thank the organizers for inviting me. Yeah, so I'm going to talk about generic subrank. Okay, that's not a good start. Guess I have to first prove that I'm literate, but okay. Okay, so I'll work over a field K. So we're going to talk about tensors. So we're going to look at a product of vector spaces. So let's say VI is an ni-dimensional vector space. And let's take the tensor product, say default tensor product of these vector spaces. So one way you can think about this, sort of more computer sciencey way, would be to think of these as, you know, arrays, d-dimensional arrays of size n1 times n2, etc. And so an element in this vector space we call a tensor. And you know, there's special tensors that are, you know, a simple tensor is a tensor of the form V1, tensor V2, etc. Where VI lies in capital VI. And so I'm going to talk about various notions of rank, but mostly about the subrank. But one most commonly used notion of rank for tensors is the tensor rank. So let me also define that. I'm sure people will use it in the remainder of this workshop. The tensor rank, I'm going to use this notation R of T is the smallest R such that T is a sum of R simple tensors. So the many applications of this notion of tensor rank in a sort of more algebraic context, you know, we know the application of the study of complexity of matrix multiplication, for example. I'm not going to say too much about that. Now, let me also, so let VI dual be the dual space. It's mostly mathematicians who care about the distinction between a space and dual space. It's again an ni-dimensional vector space. So then we can think of another way of thinking about this tensor product space, and there are many ways of thinking about it. But you can also think about it as the set of you know, multilinear maps from P1 dual plus P2 dual to PD minus 1 dual to PD. So, for example, for D is 2, then this would be just linear maps from V1 dual to V2. And a linear map has a rank. It's the space of linear maps from the dual space of V1 to V2. And in that case, the tensor rank is just the rank of a linear map or rank of a matrix. So the tensor rank is a generalization of the matrix rank. And so there are many generalizations of matrix rank, including the subrank that I will define in a moment. Now for D is 3, right, if you have T, let's say I put the dual spaces here. Sorry, if I have T inside this tensor product, you know, then we can think of T as a bilinear map from V1 plus V2 to V3. So if T has rank R, so if rank T is R, that means that we can write T as a combination of R simple tensors. So maybe write like Fi tensor Gi tensor Ci. And under this identification between multilinear maps and tensors, this tensor, this bilinear map is just given by T of X and Y is given by sum I is 1 to R, Fix times GIY times CI. So then we have kind of this formula, and this formula shows now that to compute this bilinear map, I essentially have to do R multiplications here, and then I have to take linear combinations many times. So Fi is a linear function in X, which also you also need multiplications, but just multiplications by a constant. Similarly, multiplying with this constant vector is just multiplying with constants. But essentially, you need R multiplications. So that's one way of thinking about this tensor rank. Now, I'm going to introduce another notion of restriction. So suppose T is again tensor as before. And I have another tensor, let's say S, then S is a restriction of T, and the notation will be S less or equal than T. So this is going to be a partial ordering. If there exist linear maps phi I from Vi to Wi, such that if I apply these phi's to T, I get S. And one way of thinking about that is that, for example, if S, if you view it as, say, some kind of a multilinear map, to compute this multilinear map, you can kind of use the multiplication, use this bilinear map corresponding to T. So let's look at, again, special case D is 3. So let's say, again, I'm making the duals here. If in terms of, say, bilinear maps, then S is a restriction T if there exists linear maps. Phi 1, which now goes from W1 to V1, phi 2, with W to V2, and phi 3 goes from V3 to W3, such that to compute S, X, Y, I first apply phi 1 to X and phi 2 to Y, then apply T, then I'm in V3, and then apply phi 3. So you reduce the computation of S to a computation of T, plus some linear maps. Now, there's some the very special tensors. The tensor that I'll need in this talk is this tensor that, some authors use this notation, with M. They also put an index D, because usually use D is 3, but not always. So this is basically the sum I is 1 to N, EI, tensor EI, tensor tensor EI, where we have here N factors. This is a very special tensor. Sorry, yeah, like and so now we can kind of reinterpret this notion of rank. If you think about it, the rank of a tensor T is the smallest R, such that T is less than or equal than this tensor and R. And as we saw here, the kind of interpretation is that you basically can reduce computation of T to R multiplications. And now you could also ask yourself the other way round, like if I have a tensor T, if I want to do R independent multiplications, when can I use T? When can I use that computation to one computation of this bilinear map T. So this is where the definition of subrank comes in. So the subrank T of T is the largest R such that R D less or equal than T. So again, if we are in this situation, so first of all, if you think of this tensor N, if you think about, this you can think about it as a, or let me just say R now for the moment. Right. You can think of it as a bilinear map. Right. And what is this bilinear map? It sends a vector x1 up to xr and a vector y1 up to yr. It's just coordinate-wise product. So basically just doing R multiplications. Okay. And so this means, if D is 3, this means that you're reducing R multiplications to one computation of this bilinear map. So that's some obvious things we can say. The subrank is always less or equal than the rank of a tensor. This follows from this transitivity of this relation that's easy to check, and also properties of this tensor. And one other obvious thing is, or easy to see at least, that this subrank is relatively small. So the subrank is less or equal than the minimum of these dimensions. So if you have, and maybe I should also say the subrank of this, this tensor is the same as the rank of this tensor. Is equal to n. This is some obvious, but the rank of a tensor can generally be much larger than the maximum of these dimensions. For example, an n by n tensor will have rank roughly n cubed, n squared over 3. If you take a random tensor. What are some applications? There are many applications of this notion of subrank. I mean, it's just a very natural notion. While it has been studied by people who are studying complexity of matrix multiplication, and this notion certainly goes back to Strassen and others who were studying this in the early days. And then there are many sort of like combinatorial problems that can be translated to problems about tensors, where the so some example are hypergraph independent. So some kind of like condition, like what is the maximal set of elements that don't have a certain property, Ramsey's type problems. And one I say a little bit more about is the cap set problem. I'm only going to explain like why this subrank plays a role in that case. So let's look at this cap set problem. So S here, it's sort of a problem in, I guess, additive number theory or combinatorics. So a subset is, S is called a cap set if it does not contain, say, arithmetic progression of length 3. So something of the form A plus B, A plus 2B. But actually, if you think about it in F3 to the power n, an arithmetic progression is just an affine line. And the cap set problem is, what is the maximal cardinality of such a set? Well, it's a long history. I mean, there's some obvious, the obvious upper bound is 3 to the power n. And for a long time, people were not be able to do much better than that. Like, you could prove 3 to the power n over n, or 3 to the power n over n to the power 1 plus epsilon, or something like that. And there was a couple of years ago, there was some significant progress by Ellenberg and Gijswijk. And we proved that S is all some theta to the power n, but theta is roughly 2.7551, I think. So that's an exponential improvement. But yeah, there's a long history that I won't go over. But let me just show how this subrank plays a role there. Yeah, it's an upper bound. Yeah. So if you want, you can write here less or equal then. But I think it's already in the notation, right? That this is an upper bound. So this is the big O notation. So the relation is as follows. Look at the following tensor. So we're going to work over the field F3, and D is going to be 3, and V1, V2, and V3 are k to the power F3, sorry, k to the power 3 to the power n. And the basis is given by, well, we just use, we're going to label the basis of 3 to the power n elements by the elements in this vector space. So it's a little bit confusing because the element of the bases are labeled by F3 to the power n, and the coefficients are in F3, but okay. And then you define the following tensor. You look at all vectors A, B, C, such that A plus B plus C is 0, of A tensor B tensor C. And so that lies in V1 tensor V2 tensor V3. So what is this condition A plus B plus C? Well, actually, you can easily see that A plus B plus C, right? If you have 3 elements in F3 and the sum is equal to 0, it's either all 3 are equal or it's 0, 1, and 2 in some order, right? It's kind of a funny property. So what that shows is actually that this is 0, even only if A is equal to B is equal to C, or A, B, C form a fine line. Now suppose S is a cap set, then we define phi, let's say phi I. So phi 1 is phi 2, phi 3. This is the projection onto the span of all, basis vectors where A lies in S. I mean, all the other basis vectors go to 0. So it's kind of an orthogonal projection, if you like. Though I guess that doesn't. Anyway. So then, if you apply phi 1 to tensor phi 2, tensor phi 3, to this tensor T, so what happens, like all these things go to 0 except when A, B, and C lie in S. So you get this sum all A, B, C in S, such that A plus B plus C is 0, of A tensor B tensor C. So either A, B, C lie on a line, but in the cap set, there are no lines. So the only thing that can happen is if A is B is C. So this is just some A tensor A, A and S. And basically this is just this tensor, this tensor, right? I don't know if I said this right, but if I write without an index, then it just always means these three. And so what we see is that the subrank of this tensor is at least R. Sorry, not R, in this case, the cardinality. And that's sort of like half of the work. And then is the question, okay, now we have this tensor. Now we have to find upper bounds. And you can find upper bounds by something called the polynomial methods, and using different notions of tensor rank, such as the slice rank. It was sort of introduced by Terence Tao in his sort of explanation of this proof, or his version of. Or you could also use the G-stable rank that I introduced. But anyway, but the thing about those notions of rank is that they're always greater equal than this sub-rank. And so now you have to find an upper bound for the slice rank, for example, of this tensor. Okay, but I'm not going to go into that. But you can see like where this sub-rank can play a role. Okay, so but the title of my talk was sort of generic rank. So maybe I should explain what I mean by generic. Although intuitively, kind of random means generic kind of means a random, right? If you take a random tensor, what is the subrank? But actually, generic sort of has a precise meaning here. We say a property P is true for generic P in B, or maybe it's better to say general, but anyway, let's not get too. If there exists a non-empty Zariski open subset U such that P is true for T and U. Okay, so that's all. But so it's just for some non-empty Zariski open subset. Such a Zariski open subset is then also automatically Zariski dense. If you work over say the complex or real numbers, then Zariski open also implies just open in a regular topology. So people already looked at, for example, you can ask the same question for tensor rank, and I kind of already mentioned briefly. Generic tensor in Kn, tensor Kn has rank, well, tensor rank n cubed over 3n minus 2 if n greater than 4. I think for n is 3, you get 5, I think. So this is the so in that case, we kind of know. It's, by the way, not always the maximum rank. So for 2 by 2 by 2, for example, generic tensor has rank 2, but there are tensors that have rank 3. So it's somewhat, that is related to this border rank phenomenon that I'm not going to talk about. But tensor rank does behave more oddly than the matrix rank in many ways. Previous sort of, there is a bound, or there was a bound by Strass, and Björk is kind of best known upper bound for, and actually maybe it's surprising that it's not maximal. So already, like, sorry,
QL is not
this one.
defined yet.
Oh yeah, okay, good point. I'm going to write here. Okay, so Qn1 and 2 up to Nd is generic subrank P in a tensor of size n1 time. Okay, in some sense this is I guess both a definition and the theorem, right? Because it's not at all clear that there's some Zariski open non-empty Zariski open subset for which this subrank is constant, but that's actually true. Okay, so this generic subrank, what it means is that the generic tensor. So saying that the generic tensor has rank R is the statement that a generic tensor has the property that the subrank is equal to R. Right? So in that sense.
So for this notion, you need the K is algebraically closed.
Let's say the K is infinite. Otherwise, right, otherwise, so yeah, let's say K should be at least infinite. Otherwise, you can cut out everything by some union of hyperplanes.
And also for the generic rank, if you work over the reals, it is not.
For this statement, yeah, yeah, I think, yeah, for this, and let's just say KC here for this example. Yeah, because over the real number, for example, the generic is actually not even clear what that means.
Yeah.
Yeah. Yeah. Okay. Yeah, maybe I should say PAR. Okay, so let me now say what our main results are, and then go into more details. Let's see, how can I see how much time I have? There's a big clock here, and it doesn't show the minutes. So, can I move this?
Can you speak?
Okay, this is it.
Yeah.
The minutes were just covered by some window. So all I knew, it was like it's past 10 o'clock. That's all I knew. So here are the main results. Okay. Oh yeah. Did I say this? So this QN is just short for QNNN. So here we have an upper bound. So it's basically square root of 3n. So here was n to the power 2/3. So that's like an asymptotic improvement. And we also have lower bounds, which is slightly worse, but not much. N over 3 plus 1/4 minus a half. And if you look at the difference between these two bounds, it's less equal than 5. And for small and some help of a computer, we can actually show it's equal to. Is it this part?
Yeah.
This one. Yeah. Okay. So it's actually equal to this one for small n, and also Qn. If you take, say, d copies for bigger tensors, then this grows roughly as n to the power 1 over d minus 1. So that's kind of both an upper bound and lower bound, but maybe with different constants. Okay. So let me go to the proof idea. So why is it actually not max? Why is it not NQ sorry, why is it not n? Right? It's just the problem is that if you take a sort of a generic tensor, it just has too much stuff in it. So whenever you project it down, you still have, you just want this diagonal, but you always have too much stuff intuitively, right? So, but how does But there's a big space of tensors that do have actually max, I'm sorry. Well, let me just make some definitions here. So let's see R is a set of all tensors. So I'm just going to look at n by n by n tensors from now on, such that the subrank is at least R. And we try to understand this set. Well, there's already kind of a large set of things. This is going to be, I guess, a subset here. It's all T, such that T ijk is 0 if, say, 1 less equal than ijk less equal than R, and not I is j if they're not all equal. And T I is not 0 if 1 is less equal than I less equal than R. So let me draw that this. It's easier to understand if I draw. So a tensor is like a three-dimensional array. So maybe I'll start with that. Okay, well, good enough. But these entries have to be 0 when I, j, and k are between 1 and R. So we're going to take out the little cube. Okay, so it's a big cube. I took out a little cube. But then accept the diagonal. I'm not taking out the diagonal. So I'm going to put the diagonal back in. So it's kind of, so there's sort of this diagonal here. It's kind of, let me draw it a little bit. I should have used slightly different angles, but so there's some diagonal here. I'm going to put back in. Okay, so it's a big cube minus small cube plus a diagonal. So that's this XR. So these all have rank R. And of course, this is for a very special basis, but if I change the basis, I mean that that will not change the border rank. Sorry, subrank. Okay. So in particular, if I take GLN, the GLN plus GR plus GLN, this acts on n by n by n by n tensors. In particular, so we can map. We have a map here, right? Basically, G1, G2, G3, P goes to G1, G2, tensor G3, applied to T. In fact, the image is actually contained in CR. And actually, if you look at well, it's almost like the definition, right? It actually goes on to CR. Right, because just by the definition of subrank, there should be these maps phi 1, phi 2, phi 3. And basically, they will, project onto some space. So anyway, so this is the picture. And if the border, if the subrank, of T is R, no, sorry, Q of N, then CR, right, is Zariski dense, and the dimension of CR is equal to n cubed then. So now we basically just have to understand dimensions here, and the question is for which R is going to be the dimension of GR going to be equal to n cubed. So, for example, what is the dimension of this here? This has a dimension.
All right.
Sorry, yes.
Issues was I don't understand. So you're saying that from XR you can basically go back and cover all of CR with GL.
Yes. So
You know.
so we have of some tensor is equal to R, right? But what as maps, right? If I use upper coordinate chains, you know, these phi r's are just matrices that are just, you know, ones on the diagonal, and you know that's how they look like. And so they're going to be this projection. So they have to have, you know, something like n minus r dimensions in the kernel, and then kind of projecting on this. Yeah. Anyway, if you write in a basis like that, and you write out what this means, it basically gives you something like this shape. So after coordinate chains, it will look like this. Yeah. So the dimension of this is, well, 3n squared. That's these three together, plus n cubed. But then I subtracted r cubed and then added the diagonal. And then we have to look at the dimension of the fiber of this map. So yeah, let me give this a name. Psi r. So if I take something in here, so let's look at. Okay, I'm going to take like something G1, G2, G3, T. And now this gives me something in here. And now let's look at the fiber of that. Actually, it's a variety. This is isomorphic to where we take G1, G2, and G3 to be identity, just using the symmetries that everything has. And then if these are identity, then just maps to T. But this is really isomorphic to phi r inverse T, where T is some element in XR. And so let's say sort of generic. And so the question is like how, you know, what is the dimension of that? That would be the dimension of the generic fiber. Now, in particular, this contains the set of all, say, G1, G2, G3, T, where GR is of the form, you know, has some entries on the diagonal here, the R by R diagonal. 0 is here, and then arbitrary things there. So the dimension of that is basically 3 times n minus r times n plus r. And so now we have all these dimensions here. So this is the dimension of the domain. This is the dimension of the target codomain. Well, actually the image, right? And this is the dimension of the generic fiber. And so now we have this inequality that the dimension of generic fiber, so maybe we get 3 times n minus r times n plus r is greater equal than that dimension 3n squared plus n cubed plus r cubed minus r minus n cubed. No, and then dot dot dot. This gives you then the upper bound. All right. See how I'm doing with time. Okay, so that's the upper bound What about the lower bound? It's actually for the lower bound, we actually use kind of the same picture. But instead of so what does it mean that this is, well, this has dimension n cubed, right? That means that the differential, at least at the generic point, this differential is going to be surjective. Okay, so let me put this here. So we can choose some generic enough t in XR, and now we can look at differential at this point t. For the Lie algebra of GLN, the tangent space at identity. So I guess what I'm doing is actually take this at the identity t. And again, if you don't, you could take it at other group elements, but we have symmetry, so might as well look at this one. No, the identity kind of looks like t's. Okay, anyway. So the tangent space at the identity, which is Lie algebra, is just K n by n matrices. And then the Lie algebra at T, maybe we call it YR, but YR is almost the same as XR, right? Except that XR is not a subspace because I said this is not equal to 0. That's not an equality. So that, but if I just would remove this whole condition, then I think you just get YR. Right, that's just a tangent space. But so it kind of looks the same, and this goes to n by n by n tensors. So this is just a cube. This space is again this thing, but now without this cube. But again, we plug in the diagonal, although we allow zeros to be on the diagonal now. And these are just matrices, right? And so what is this tangent? So it's now kind of a direct sum of vector spaces. And now if you restrict to this here, it's just identity, right? If you restrict just to this tangent space. So clearly you're going to get everything in here outside this little cube, right? So the only thing that really happens is within this small cube, we have this diagonal, and there's some map of these three matrices into here. And then there's maybe this little diagonal that plays a role too. It boils down to the following problem. So if A is a subspace of, say, R by R matrices, then I'm going to write A bracket 3 as a subspace of R by R tensor. But I'm just going to take this A tensor KR. Okay, so I just kind of tensor with any factor here and take span of that. And similar, if you take A1, I'm kind of put the KR in the second position, first position. And then also A2, that's kind of hard to write down because then A is going to be spread out over the first and last position. So you could say it's this A1, but now you switch these two positions. So that is kind of okay. So and then also define, say, WR, say set of all tensors, such that Sijk is 0 if I, J, K are distinct. And so then we get that following result. If A, B, C, K, R by R of dimension n minus R, and A1 plus B2 plus C2 plus this WR is K R by R, then Qn is subrank is at least R. So this is how we get lower bound. And so these conditions, this A, B, and C, they kind of come from this from this action. And so the condition on these tangent spaces in this cube is going to translate to this. So this should be true for some A, B, and C. So if it's true for some A, B, and C, then it's also true for generic. But actually, this turns out to be pretty hard to check if this is true. So there are some kind of question, and I see I have to stop. But so yeah, maybe we'll just stop here. Oh,
can you say anything about? You mentioned this is related. Is subrank related to latest multiplication? Like whether they come out? What's the?
Yeah, I think it comes up in many ways. So I think it was proved that this, for example, for the matrix multiplication tensor, sometimes denoted by this is that the subrank is less or equal than, was it 3/4 n squared? I think if you go to border subrank, which I didn't define, I think you have equality. But I think it also comes up in if you want to, I think if you want to find obstructions for certain constructions, matrix multiplication.
But also in algorithms, which often when people make algorithms, the matrix multiplication algorithm is when you start with a diagonal tensor, and you do this restriction to a matrix multiplication tensor. But that would be a tensor in our path. But many of these algorithms, they don't give just a matrix multiplication tensor, they give a matrix multiplication tensor with some other tensor. The other tensor is kind of useless, doesn't do what you want to do. But then if that other tensor has a good subrank, it's a high subrank, then you can have a restriction from that other tensor to a diagonal tensor again. And then you can reuse the diagonal tensor to make more matrix multiplication. You get this recursive structure. So yeah, so in construction is actually.
So these are the way thing that I was telling.
Yeah. And then the other direction that Mark mentioned, the obstruction direction, which is this whole co-precision.
Does it appear on Schoenhagen's asymptotic summing equality? Will you use it there? No. Okay, that's fine.
But all these co-precision constructions, you can, like, they make use of some sort of special tensor. Yeah, you can use this subrank to analyze whether this tensor is good for getting good upper bounds. Maybe one comment, like the open problem is whether this subrank is actually computable. Like, we don't know. That's kind of surprising. Like many tensor notions are hard to compute, right? Tensor, of course, etc. But this is one, like subrank seems very natural, but we have no idea what the complexity is.
Why is it natural? The generic tensor doesn't have maximal rank. It's something very strange.
Yeah, that's your rule for it.
It's something I would expect.
I don't know. Yeah, it's. I mean, there could be other notions that are generic and very easy to value.
Essentially, all notions of rank will be sandwiched between rank and subrank. In that sense, it's very important.
Oh. I think I forgot to mention something important, that this is joint work with this joint work with Visu, Makam, and Jeroen Zuiddam. And so when I was talking about main results, these are our results. Just to be clear.
For the three-term arithmetic progression tensor, it was not known that the subrank is at least this 2.755.
So for the capsule problem?
Yeah, for the capsule problem, do we know the subrank of the PAT tensor?
No, we don't know that.
No, as a topic subrank.
Oh,
So one could not improve on this 2.755 with Subrank. It's lower order.
Well, I mean, there are slightly better bounds, upper bound for the, you can divide by square root n.
Yeah.
But I see, but
They have the same like, isn't it?
yeah, yes,
As far as I understand, there's like a sort of filtration of the ambient space by subranks.
yeah,
I may fix the subrank, and then there's a variety of the tensor of the subrank really within that number.
yeah,
And then I can make, if I fix all the subranks up to the generic one, there's a whole filtration of the ambient space with these varieties, right?
yeah. I mean,
So the question is if there's a relation between this filtration and the one via the rank, the tensor rank. Because from the geometric point of view, the tensor rank is a very natural description, but this subrank, I mean, the variety, you describe the CR. The CR is the one that fills the ambient space.
yeah,
But if you fix a smaller subrank, then you get another set, you may close it, then you may get another variety, right?
Yeah. Now, when you say by fill, you mean like dense, right? Yeah. Okay. But yeah, I think they look quite different. So the rank and subrank, although one is bounded by the other, but you see, yeah, some cases they're very close together, and sometimes they're very far apart.
I have a small comment, just in case people didn't notice. So in quantum information, this unit tensor is known as Greenberg-Rowan-Seilinger state, or GFC, and the C of GFC just got notified in part because of this thing. So if you go to the Nobel Prize website and you read about the Nobel Prize and why it gets the Nobel Prize, one of the reasons is actually this GFC paradox. And it's very far away from this.
Oh, that's okay.
I think, we get back here.